Hello everyone and welcome to CSCI 343 Fundamentals of Data Science. Today we're going to be picking up our discussion with descriptive statistics. Don't worry, it's not as scary as it sounds, and a lot of this you already probably have some familiarity with. So, with pretty much anything, I like to get started by telling a story. So, when I was a kid, my favorite part of the week was actually going to the grocery store with my mother and grandmother every Friday without fail. They would get together and they would go to the Piggly Wiggly. And they would go and they'd get their groceries and then they would leave. And when we'd get finished, we'd get in the car and we'd go to a fried chicken place. And we'd get in the drive-thru and we'd order some buckets of fried chicken. And a good old Southern Friday, we're going to have buckets of fried chicken. And when they get to the place where they need to cash out, they get in an argument about who's going to pay for the fried chicken. And, that was pretty much the par for the course for a Friday, You get up, grocery store, fried chicken. But every now and then something special happened. Something unexpected. Something amazing. And that amazing thing was... samples. Every now and then, and Lord knows why it would happen, but you'd walk into the grocery store, and at the end of every aisle would be a little tiny table, with usually a little old lady, and a series of samples, and they would hand them out to folks, and you'd try them, and be like, oh, this tastes good, maybe I'll buy it. And the most amazing thing about sample day was, especially when they had sausages, because what they would do is they put the little tiny pretzel stick in the sausage, so it was like both an eating instrument and an additional little snack. It was wonderful. It was glorious. It was the best thing to happen to a tiny little kid, frankly. Sample day was great, but I had a problem with sample day. Sample day had one fundamental flaw. And that flaw was you were only allowed one sample. And the problem that I have with this isn't that I want more sausages on little crunchy sticks. The problem with one sample is, how do I know you just didn't give me the best sample out of the bunch? How do I know the rest of this food is going to taste as good as this delectable smoked sausage that you just gave me? Well, turns out this is a real problem. And it's something that's fundamental to statistics. What we try to do when we're collecting data and running analyses is we're trying to describe not how good or how big or how bright a single thing is. We're trying to describe a population or a group or a set of things. And the problem is, we can't measure everything. And this is the problem that the grocery store kind of runs into. They don't want you eating all of the samples, otherwise you've eaten the stock. So what you try to do is get a representative set of samples that will tell you something about the population that you are sampling. And ultimately, this is what we're doing in almost all statistics, is we're trying to represent something larger from a smaller, more manageable set of samples. For instance, we can measure the height of everyone in this room, and that's fairly manageable. And that might give us an average height of, students, say, in the U.S. But if you want to do the average height of people in the U.S., you'd have to measure all of the people in the U.S., literally every person, if you wanted the exact average height. But that's not feasible. So what we try to do in statistics is try to approximate characteristics of a large population based on a smaller set of samples. Now, we hinted at this last class meeting, and turns out this is actually something that's really, really important and very fundamental to statistical analysis. Notice, and again, we talked about this in our last set of examples, and I'm trying to move my pointer on the screen there if you can see it. Remember, we had about 50 samples in this one, and this looks something like a normal distribution. And we had maybe a couple hundred in this one, and it's getting closer to a normal distribution. This one probably had a few thousand samples, and it's looking more and more like a normal distribution. Here's our Matura example where we've got something that's very, very, very close to a normal distribution. So the more samples you add, the closer you approximate the characteristics of the population, the closer you approximate that normal distribution. And as you approach the number of possible samples or the number of people in a population, like an entire group, the closer you're going to get to the distribution that is fully representative of that population. But again, sometimes those populations are so large we can't reasonably measure them all. So what we want to do is find some subset of the population that will be representative. And there's a wonderful cheat that we use all the time in statistics. And it's the fact that as you collect more samples, you approach that normal distribution, which means if you get enough samples that you've got a good approximation of the population distribution, you don't have to measure the entire population. This relates to something called the central limit theorem. And in a nutshell, it says that the more samples you take, the closer you approximate the normal distribution. It's essentially you end up getting towards the limit, approaching the total population distribution. Now let's look at some real actual data. So as we've talked about in here already, we use a program, an AI, to check your submissions for your assignments for cheating. And here is the output of one run of that. This is actually from the first semester that we used this method, and it's just fantastic. This is just an awesome data set to use. And notice, the y-axis is our program similarity, and the x-axis are anonymous student IDs. You don't know who these people are, but you definitely notice that there's sort of a pattern. If you look at it across the bottom, we've got similarity, around 20-ish% less most of the way, and then it starts edging up a little bit and then shoots all the way up to the top almost to 100%. So as a matter of fact, I've got a dotted line there at 90%. So these up at the top, you can kind of say that there's probably something fishy going on there. Now if we plot this differently, instead we plot how many submissions fell into 10% blocks or something of similarity, we get something that looks like this. Now this looks kind of cool. Now, again, this is like about 50-ish students. So we don't expect to see something that's super, super normal-ish looking, but you can definitely see something that's beginning to look like a normal distribution here to the left. And then you've got this odd spike out here to the right. Well, something interesting happened. Remember, we were talking in our last class meeting that when we collect data, we're trying to measure a thing, usually, like a single thing. And we want to look at that raw data to see if it looks normalish. And if it looks normalish, then we're probably at least on the right track for measuring, what we're trying to measure. But every now and then, you end up with something unexpected. Kind of like that little jump and dip in the Matura example. We have something unexpected here. We have something that's beginning to look kind of bell curvy, and then a giant spike out here on the side. What the heck's going on? Well, usually what this means is that you have outliers in your population. Members of the population that don't conform to the typical normal distribution. Now, this could mean several things, but usually this means that you might not be measuring what you think you're measuring. You might be capturing multiple signals, so to speak, in your data collection. And these group of radically different measurements are often considered outliers. Now, outliers tend to bias your data. So the outliers could be different due to just random chance. They could be different due to them relying on a different method or strategy than the rest of the group was relying on, but somehow they're different than the majority of the rest of the population. And outliers can significantly bias your analysis if you're not aware of them. So we have to take those into account when we're doing our statistical analyses. So if we look at this, we can kind of say that we've got two populations. So now we've separated these guys out. with one being our group of most of the students, and the other one group being our group of those that were potentially, we'll say, potentially violating our code of conduct. And when you look at it like this, it's no longer ambiguous. It's actually super clear that something fishy's going on. That, on average, you know, uh, similarity is going to be, somewhere in this area just by random chance. But then we have a small group that's very tightly packed over here on the edge that have very, very high similarity in their submission. It's obvious that we have two populations. Now, when we give you assignments, what we want to do is we want to measure your understanding of the topic. In this case, we're measuring your understanding of a topic based on how well you perform on assignments or quizzes or tests or whatnot. Well, sometimes we accidentally pick up another signal. And that other signal, in this case, isn't the work that the students did on the assignment, their knowledge, but instead their ability to duplicate it from someone else. And like I said, this pops out very, very clearly in our software similarity analysis. So, dramatic pause. Followed by, this is my not so subtle way of telling you that you don't need to cheat in this class, because you're almost definitely going to get caught. It's really important that you actually do the work yourself, because our software checker is really, really, really good, and it's not going to be fooled by your typical attempts to obfuscate your code. It figures this out. It's way better than any human is at detecting similarity in source code. So please, please, for all that's good, don't duplicate code in this class. And we actually keep copies of all the submissions from previous semesters, and when we do this analysis, we run your code not just against your peers in the class, but your peers in previous generations of this class. So please, please, don't cheat in here. It's really not worth it. Because honestly, one of the things that I want you to get out of here is experience doing a thing. And if you duplicate other people's code, that's not, you're not getting that experience. I'd be much happier with you if you got a D in this class and actually did the work yourself, because then you actually learned something, than I would if you got an A in here and didn't do a darn thing. The whole point of doing this is to learn something new that you can take out and apply in other aspects of your life and your career. So please, please don't cheat in the class. But, it's none of my business in the end, is it? Well, it kind of is, and at least briefly. For the rest of your life, it's none of my business, but in this class, it's my business. Okay, so populations and outliers, moving right along. So, since we can rely on the fact that these normal distributions tend to form and get closer and closer to actual large population distributions as you add samples, we can tell certain things, certain properties, certain characteristics of our population based on our sets of samples. One of the things that we often do is we take averages. Averages are a way of describing the center of our distribution. So if you recall from our previous set of lectures, and we're looking at the blind walking examples from the virtual reality studies, we could tell that on average, people in VR walked, like 60, 70-ish%, whatever our numbers were. People in the real world walked about 90-ish%. And we could tell that by looking at where the center of our normal distributions fell. So that's where the average for our population would be. There's a couple different ways that you're probably already familiar with of determining averages. One is called our mean, another is our median, and others are mode. Each of these are important, and especially for different kinds of data and different situations. So let's talk a little bit about those. Mean is what most people mean when they say average. So if you talking to someone casually and they say, oh, well, the average blank was whatever. Usually what they mean is the mean of whatever they're talking about was whatever value. The code for this is given in the book, but it's pretty straightforward. You add up the values from all of your samples and then divide by the count of samples that you have, so the total number of samples. Now, this is useful, but it's typically most useful if your series of samples is very homogeneous, meaning you don't have multiple distributions in your data. So, for instance, if we look at our software similarity example, we clearly have two populations. We've got one group over here, and we've got another group over here. If we average them all together using a mean, what we get is a value somewhere around 35-ish% similarity. And as you can tell by looking at our distributions, that's nowhere near the center for most of the class. So this is not a very homogeneous population. So if you have data that's noisy or has a lot of outliers in it, the mean might not be the most appropriate way of estimating where the center of your distribution is. So, what do we do? Well, sometimes a better way to figure out the center of your distribution, especially if your data is noisy, or you have a lot of outliers or something like that in it, is to actually look at the median. The median is a special kind of average where you're not necessarily, getting the sum of things and dividing it by some number. You're actually looking for the tipping point in your data. So the point at which 50% of your data lies above this value and the point where 50% of your data lies below this value. And the crazy thing, though, is that the median, how you figure it out, changes depending on whether you have an odd number of values in your set of data or an even number. So remember, we're finding the tipping point. So where 50% of your values lie above and 50% of your values lie below. If you happen to have a data set that has an odd number of values, this is pretty easy. You sort your data from least to greatest, and then you get that middle value. So in this case, in this example that we've got here on our slides, we sorted our data and from least to greatest, and the middle value is 7. So 50% of our values are above 7 and 50% of our values are below 7. What if we have a circumstance where we have an even number of samples? Well, this isn't too much more complicated. You find the middle two values and average those two together using a mean. So you sum those two values together and divide by 2. And so you get 9 in this particular case. And the 9 is now the tipping point where 50% of your values lie below and 50% of your values lie above. Now, this seems like sort of a weird and maybe unsophisticated way to figure an average. Well, it's more sophisticated than you think. So if we look back at our example with the software similarity, what we find is if we look at what the tipping point where 50% of our values are on one side and 50% of our values are on the other, we end up with something that's way closer to the center of our distribution for the majority of the class. And this is with the outliers still included. So this is one of the powers of using a median to figure out the center of your distribution. It's less sensitive to noise in your data, and it's less sensitive to outliers. Is the median still biased by outliers? Yes. Is it biased as much as means? No. Ideally, if this set of data didn't have outliers, but instead we had a single homogeneous population, the mean and the median should hypothetically be the same thing because they both will then define the center of your data. Another average is mode. Mode is typically used when you have something that can't necessarily be quantified on like a continuum. The example I like to use is a can of mixed nuts. You can get the average nut out of a can. And in this case, in a lot of mixed nuts, you'll have this thing on the front that says less than 50% peanuts. Well, guess what? It's probably going to be the average nut. More often than not, you're going to pull out of that container. Probably going to be a peanut. So if you have things that fall into like discrete categories, modes tend to be more useful. So if you got out all of your nuts, from this container, and you stacked them up in a line, your line of peanuts would probably be longer than say your line of macadamia nuts, and definitely longer than your line of pecans. Because let me tell you, most mixed nut cans are stingy on the pecans. Let me tell you, that's my favorite nut. I love a good pecan, especially at Christmas time when they're like roasted and sugar and spices, and you it's just like that's the flavor of the holidays for me. I love them. So, um, yeah, yeah, so that's pretty much what I was already saying. Yeah, it depends. The situation when you want to use a mode depends on the kind of data that you're looking at. If everything falls in nice little neat discrete bins, mode will tell you the most frequently occurring thing. But typically with continuous data, it's difficult to reasonably use mode, especially if it's fractional data, because you never end up with something that's exactly 1.379 or something like that. But our distributions have other characteristics as well. So our averages tell us about the specific characteristic of centeredness. What is another characteristic? I would typically ask the class. And the answer to that is our distributions also have a width to them, a spread. So notice, for our outliers here, that population is very, very narrow. So almost all of the members of that population fall in a very narrow group. While for the rest of our class, it's a much wider group. It's much more spread out. So the spread of our populations are often referred to as dispersion. And this pretty much describes how spread out that distribution is going to be. There's a couple different ways of describing, statistically describing dispersion. A common one is called variance. And this is essentially the sum of squares of the difference between our samples and the mean of the population, or its center. Now, this is an easy thing to calculate. It's very easy to compute. I'm actually going to try to teleport over to our marker board and show this to you. So let me switch my camera, and okay. So here we are at the marker board. Let's see how this works. This is my first time using this live in class. Okay, so our variance is described like this. We have the sum of the difference between a sample point. So some value I, we'll call it. And then subtracted from the mean of all of our samples. And that value squared divided by the total number of samples that we have collected. Now, this is a fairly simple equation, and it should look a little bit familiar to you. Why? Stay tuned. Now let's switch back to our slides for a moment. There we go. Now, one of the disadvantages of using variance is it's not a very intuitive unit. You end up with whatever unit you've measured squared. So if we're talking about software similarity, what does similarity squared mean? It's a little bit difficult to interpret. So another way of looking at this is perhaps a more common way of measuring dispersion called standard deviation. And standard deviation is simple to compute if you know the equation for variance. It's just the square root of your variance. Now let's switch back to our marker board for a second. And grab our marker. And so we take the square root of this whole thing. And that would be our standard deviation. Now at this point, this should be looking very familiar to you, and maybe not for the reason you think. This looks very similar to something I can guarantee that you've seen and been taught in in some of your math classes that probably weren't statistics classes. As a matter of fact, this looks a lot like an equation that you're probably all very, very familiar with. Wow, it's amazing. Erasing the marker board in VR is just as tedious as it is in the real world. Here we go. So let's switch our colors up here just for the sake of having a little bit of fun. This might look very familiar because it looks a lot like this. It looks a whole heck of a lot like, what is this? Do you recognize it? It looks like the distance formula. Matter of fact, our standard deviation is almost, not quite, but almost exactly the same as your distance formula. And that's not necessarily a coincidence. You can sort of think of standard deviation as being the average distance between the median and the other point, or the mean and the other points of data within your data set. So sort of the average spread, the average distance. Technically, they're not the same thing, but it's a good way of conceptualizing it. And the mathematics are actually very, very similar to each other. So, there we go. So yeah, as it says on the slide, this looks familiar. So like I said, you can conceptualize your standard deviation as being like, it's not technically the same thing, but like the average distance between the center of your distribution and the other points within your data set. Another way of looking at the spread within your data is looking at quantiles. And usually we think of this in terms of quantile ranges. Like one that you're probably familiar with is the interquartile range, where you're looking at the range of values that fall between the upper 25% and the lower 25% within a data set. You see this a lot on things like statistics for like standardized exams, like you took like in high school and elementary school. And we talked about a very specific quantile earlier, and that is our median. Technically, our median is a quantile, but it's a very specific quantile. It's the quantile for the 50% range. So it's the value below which 50% of your population falls. We can also have a quantile of any other value. So we can have a 25% quantile. So the value at which 25% of your population is below and 75% of your population is above. Another characteristic of data is correlations. Correlations deal with how two sets of values, two variables, change relative to each other. So if two variables, two things you're measuring, change in correspondence with each other, they vary along with each other, they co-vary, you have a correlation, or a correlation. So, for instance, in this example here, we have what's called a positive correlation. And we have the price, the cost of my electrical bill. These aren't real numbers, by the way. They're real. They're based on real values, but I've finagled with them so they're not exactly representative anymore. To better illustrate, our example. So along the x-axis we have the temperature outside, and along the vertical axis we have how much my electrical bill is. We see a very strong positive correlation. A positive correlation means that as one value increases, the correlating value also increases. So we can clearly see that as temperature goes up, so does my electrical bill. And if we look at this, just out of correlation, we can tell some interesting things about what something that we're measuring. In this case, we're looking at month of the year along the x-axis and bill value, how much I'm being charged, across the y-axis. We have my electrical bill on this side and my gas bill on this side. Again, based on real data, but jiggled a little bit to fit better for an example. And by looking at this, you don't know a lot about me, you've never been to my house, but just by looking at this, you can make some speculative, have some speculations that might not necessarily be very inaccurate. For instance, you can probably look at this and guess, well, his gas bill is high in January through March, and it goes up a little bit in December, and it's really, really low during the summer months. So chances are Dr. Jones has gas heating in his house. And similarly, if you look over here and you see my electric bill is very low during the winter months, very high during the summer, you can say, oh, well, he's running his air conditioner. Probably, who knows? And you would be correct. Now, this is an example of a positive, or this is the example of a negative correlation. So when things don't vary with each other one-to-one, but instead are the mirror of each other, this is called a negative correlation. So as one value increases, the other value decreases. Now, the important thing to say about correlation here is that correlation doesn't imply causation. Now, you've probably heard this phrase a lot. What that means is just because two things seem to change in concert with each other doesn't mean one of them causes the other one. For instance, a really great example is as people consume more ice cream, more people die of drowning. Oh my goodness! Obviously, ice cream causes people to drown. And if you pose this question to an audience, like why is that? You're going to get some really interesting answers, which makes sense because the way you frame it makes it sound like ice cream is directly related to drowning deaths. And you'll have people say, well, they obviously went swimming within 30 minutes of eating their ice cream because you're not supposed to do that. Well, not necessarily the case. Turns out ice cream consumption and swimming deaths are related to something. They do have something in common, and that's heat. So the hotter it gets outside, the more likely you are to go swimming. The more likely people are to go swimming, the amount of people who drown go up. Similarly, if it gets hotter outside, people are more likely to engage in eating a nice, cool snack in the form of ice cream. So these sort of correlations between things like consumption of ice cream and drowning do not imply that one causes the other. Ice cream doesn't cause drowning, and drowning doesn't cause ice cream. But they have a causal link. So they're both being driven by another factor, in this case, how hot it is outside. So keep in mind, that, for instance, the example here, my low gas bill was not caused by a change in my other bill. It was the temperature outside affecting these things. So always keep that in mind, that just because things correlate with each other doesn't necessarily mean that one of them caused the other thing. We have to be very careful about making statements like that. Okay, so we're going to wrap up our discussion of descriptive statistics with this. These things will definitely be on a quiz in this class, so study those things, memorize them, write them down. And if you have any questions, please let me or our class TA know. Otherwise, stay happy, healthy, and safe, and I'll see you in cyberspace.